Now let's look at normal forms, what they are and how to achieve them. We already see that the number one issue we encountered was non-atomic value. In this example, it's a repeating group. How do we achieve a state where we do not have any atomic value? If each column of the table is a single value, then we say table achieves first normal form, which means if there's no repeating group or nested value, then the table is in first normal form or is first normal form compliant. How do we achieve first normal form, however? We will use a decomposition to break up the non-atomic value. We are going to create new relation with the non-atomic value broken up. So for repeating group, for the first scenario of a non-atomic value, the repeating group, we will break the repeating groups into separate rows. So for each element of the repeating group, we will break it into the separate rows of the new relation. Meanwhile, we will also merge the original table's tuple. It says the primary key, but basically primary key and all its a dependency, right? We say with the primary key, but basically it's a primary key and all its dependencies of the original table into these separate rows of the new table. So for repeating group, you have multiple elements, right? Multiple elements inside this repeating group. You will have each element as a new row of the new relation or new table. Meanwhile, you will also add the primary key and the dependencies, which basically means all the values in the original table into the new relation together with the repeating group elements. The new primary key, the primary key of the new relation will be the original primary key plus the repeating group's primary key. For nested value, you will break the nested value into separate columns. The new primary key will be the original primary key plus the nested entity's primary key. So for repeating group, we have this course. Right? The course is a repeating group. We have two elements here. So we will break these two elements into two rows in a new relation. Then we will add the original table's content into this new relation so that it forms a new relation of both the original table value and one of the elements in the repeating group's value. Each one element of the repeating group's value, right? So you are forming a new relation by creating one row for each element in the repeating group, plus whatever used to be in the original table. This is how you create a no repeating group relation. For nested group like this one, course name and instructor, you will break up this course name and instructor into two columns and form a new relation. Then you also need to add whatever was in the original table and form this new relation of the original table plus the columns that was broken up, and the new primary key will be the primary key of the original table and possibly end with this primary key of the new table, of the new, the broken up columns, if there's any dependency. So this is how you achieve first normal form. Now, what if the primary key? So now that we have first normal form, we have the primary key, we have every single value is dependent on the primary key, right? But what if the primary key is a combination of columns and some columns are only dependent on one of the columns? For example, here, instructor and the tuition are dependent on course name. It's not dependent on student. And the student address are dependent on student name. It's not dependent on the course. Just because you choose a new course, you're not going to move to a new place, right? So the address is dependent on student. That's the function, that's the redundancy we encounter, right? Because for each address dependent on student, when you have new course, the address is student dependent on student. For the same student, you will have, for same student, different course, you will have the same address repeated. This is redundant. This is what we call partial dependency. Address, city, state, zip are functional dependent on student name. So they got to repeat it. In order to achieve a better data integrity, we need to remove this partial dependency. If a form is already in first normal form and does not have partial dependency, then it's in second normal form. What it basically says is each non-key attribute is dependent on the whole key, not just part of it. Note here, we already said it's dependent on all whole key, not just a part of it. If you only have, if your primary key is single column, if you only have one column in your primary key, there's nothing called part of it. The key is the whole key. There's no part. So in this case, if you are already in first normal form and you only have a single column, then it's automatically second normal form compliant. However, if you are in first normal form and you have a compound key, you need to check the non-key columns to see whether they are really dependent on the whole key or just a part of it. If there's a partial dependency, you need to do decomposition. In this case, we'll just break up each group of dependencies, the partial dependencies, into a new relation. We will break up each group of dependencies into a new relation. Each partial dependency apparently will be a new relation, right? If you like address to student, this apparently is a student relation. But then very importantly, and this is a common mistake, you need to make sure the original dependency on the compound key is still there. You still have the original dependency on the compound key. Don't miss out any dependency. It says because it's very easy to forget there's an original dependency on the compound key, especially when there are multiple dependencies. Here, partial key itself has a dependency, right? The partial keys, like in our example, we have the primary key is a compound key. We have the student name and the course name. Partial key like a student name itself has a partial dependency on it, which we will break out. But then student itself is a part of a compound key. You still need to keep the compound key so that the original relation is still there. Let's take a look at the example. So in this case, we already have a student course name as a primary key for the registration, right? This is already first normal form compliant. There's no repeating group, no necessary value. Now, address, city, state, zip, dependent on student name. So we will break it up into one new relation. And the course instructor and tuition depend on the course name. So we will have partial dependency. We have a partial dependency on that. We will break a new relation into course, right? We will break a new relation called course. Now, student name and course name, it itself is a primary key. You still need to keep this primary key. You still need to keep this compound primary key as a relation because there's still this relation, this dependency between student name and the course name. If you remove any student name and course name, you are removing this relationship. So remember, there are three dependencies here in the original first normal form compliant table. You have the student name, you have the student name, partial dependency. You have the course dependency. You also have the student name and the course name partial, this dependency, right? So make sure each time you see a compound key, make sure you identify the partial dependency and make sure you remember there is still the original relation that once you break up the partial dependency, this original one is still there. This is the most common mistake I see in normalization, that you forgot student name or forgot course name. Of course, now that you see that, it's easy. But once you are facing a compound key yourself, it's very easy to forget there's a primary key, there's a compound primary key there, and you need to keep it. Okay, now let's say we remove all the partial dependency. There's still one common issue, which is called transitive function dependency. What if is called A is some functional dependent on a non-key column B, and B is in turn functional dependent on another column C, which means, for example, here, instructor affiliation is dependent on a non-key column B, instructor, right? Instructor affiliation is relatively stable. It's not just because I take another course. Let's say I'm teaching DS530. If I start teaching DS610, it doesn't mean that I will change my affiliation from Jedi to this. Right. So right now, instructor affiliation is functional dependent on instructor. The problem is instructor is a non-key column, and non-key column is functionally dependent on the primary key. So this is transitive dependency. Affiliation is not functionally dependent on course name. Instead, it's dependent on a non-key column instructor. The issue is, of course, now that I have multiple Jedis in this table, if I need to change something, let's say this is Anakin Skywalker, and I need to change the instructor affiliation to this, right? Then I need to change this in multiple places. That's the duplicated data, the data duplication we talked about. If a table does not have any transitive dependency, we say it is third normal form dependent. Third normal form compliant. Third normal form, a table is in third normal form if it is in second normal form and has no transitive dependency. Then how do you remove transitive dependency? You will do the decomposition by breaking up each dependency into a new reaction. Note that this is the same as how we do decomposition in for second normal form, right? At that time we said same thing. How do you make sure it's second normal form compliant? You will break up each dependency into new reaction, sorry, that's not reaction, relation. I have to change that. But yeah, transitive key and its dependencies. The transitive dependency will go into will be broken up into another relation, while the original primary key and its dependencies, including the transitive key column, must stay in the relation. Now, another common mistake is that students, when they create a new relation, they will happily remove the transitive key and the dependencies into a new relation. And by this, they also remove the transitive key column away from the original table. But remember, transitive key column does have a dependency on the original primary key. So you must keep this relation. You cannot remove the dependency of a transitive key column and the primary key column. So we have this course name, tuition, instructor affiliation. If I want to break, I see this as a transitive dependency, right? We already identified this as a transitive dependency. So I'm going to break this up into a new relation, which is instructor. Now for the course relation, do not forget that instructor is also dependent on course name. So you do need to keep this instructor in this course relation, right? So now you have two relations. One relation is the instructor, another is a course relation. And you need to have the instructor column in the course relation, because instructor attribute have a dependency on course name. Don't lose it. Don't lose it when you when you move the transitive dependency. Okay, so now that we are third normal form compliant, you sometimes will hear the name of Boyce-Codd normal form or BCNF. BC normal form is an enhancement of third normal form. It basically says all non-trivial dependencies are on table key. Trivial here means self-referencing. Now, BCNF only happens when you have multiple compound candidate keys. You have multiple candidate keys and they are all compound, and then you might have an issue with the BCNF. This is very rare. I have usually in real world, most third normal form compliant designs are already BCNF compliant. In my personal experience, I have never encountered any form that is BCNF, that is third normal form compliant, but not BCNF compliant. So we will use the term 3 normal form to reference both third normal form and BCNF in this class. Usually you don't need to worry about it. This is one of the 2 derived forms that we mentioned in last session. So in all, normalization is all about function dependency. As we said, the issues with the original poor design was with function dependency, the poor parsing of functional dependency. And further down is about the functional dependency on primary key. So the first normal form basically says all elements must have a key, must be dependent on the primary key. We call it the has a key, right? All elements must be atomic, meaning using the primary key, you can immediately determine the value, right? Which means all element has a key. A second normal form is dependency is on a whole key, not part of it. And third normal form says all dependencies are only on the key, not on any non-key column. So we are still talking, when we talk about this 3 normal form, it means all element has a key, on a own key, on a whole key, and only on the key. Remember these 3 parts in red. So normalization is the most common, is basically printed in the blood and genes of relational model. But normalization does not always mean that you have to break relations as small as possible. In fact, sometimes a lot of normalization also have its downside, which means it may cause performance issue. If you have too many small tables and you try to get data for a whole picture, you must read from multiple tables and combine them together. Now this can be a performance hit. So not normalization, that's when we say, why don't we want to go to 4th, 5th, 6th normal form? Because the effort you put into normalize into this extent, into these smaller normal forms, and the gain you can get, it's just not worth it, not worth your effort. As also, even if you go to third normal form, the performance, you are still breaking up a table into smaller ones, multiple smaller ones. And when you want to get the whole picture, you want to get all the columns together, you need to pull all these tables in and put them together. And this can be also a performance hit. So there are only so much you want to do when you come to normalization. In fact, in certain scenarios, you don't want normalization, you want to denormalize. You want to put a normalized model back, roll back a little bit. So make it is not, it has maybe have a transitive dependency, maybe have a partial dependency, just so that when you want to pull the data, you have everything, right? So one example is a state and zip relation. When you think about state and zip, what's the relationship? A zip can functionally depend on a state, right? Because at least in United States, each state have multiple zip code and each zip only belongs to one state. So this is actually a dependency. And you can imagine in most of the address table, zip code, a state is dependent on zip code, and zip code is not going to be the primary key. Usually in the address table, the address itself is a primary key, or maybe the customer or customer version. It will be the key, and zip will be a non-key column dependent on the primary key, on the address primary key, and state is functionally dependent on zip. So this is a transitive dependency, typical transitive dependency. However, if you want to make a third normal form compliant, you will break this address table into two: the address table up to the point of zip, and the zip state table. And every time you want to pull address, you need to pull data from two tables and join them through zip code. Now, when you consider the issue, why do we say we don't want to have the transitive dependency? Because it will cause redundant data, right? But you are normal, and the issue with redundant data is for its performance. When you try to update, when you try to change, it will be issue, and it occupies some more space. This is the issue with redundant data. But if you consider like state, usually in a zip code table, in the address table, state only takes two characters, or with a comma. State only takes two characters, or with a space between city and the state, then it's three characters. Even if you are repeating this, the cost of storage is minimum comparing to what you actually have for address, right? This is 3 character per address, comparing to what you have for the street address and the city name. The impact is minimal. So address is not so much as a concern. I mean, storage space is not so much as a concern. And talking about update, I have never heard the United States Post Office changing any zip code or state. They will only annually, never ever change zip codes and state relationship, right? So if there's ever, and I think all of you assume this will be the same way, and there will be no change in the zip code and the state relationship. So we do not expect any change. So in this case, the two concerns that we have for redundancy data, the update issue and the storage issue, are all proved to be trivial. Then why do we want to still break it up into two tables, suffer the performance hit when reading, just for those two trivial concerns? The two concerns that are already proven to be trivial. So there's no need to do that. That's why when you look at the address design, usually people will just put zip code and state together in the state table, in the address table, although state is functionally dependent on a non-key column. It's not third normal form compliant, but this is a common practice. Still, a common practice is to have this non-third normal form compliant design. Zip and state will stay in the same address table instead of being breaking up. So this is one good example of denormalization. It by itself is trivial and it's intuitive, but I want to go through this so that you understand that normalization, the aim of normalization is for a better, for data integrity and performance. And for the same reason, we may want to do a denormalization. There are other reasons that you will do denormalization, like other scenarios that you will do denormalization, like a data warehouse, like unstructured or semi-structured data, like in non-SQL database. We will talk about all this in future sessions. But before that, and except for the zip state code, zip state code exception. Other than this zip state code exception, and before we talk about those unstructured and the data in the data warehouse, we will still do everything to third normal form, because in most cases, 99% or 95% of the cases, third normal form is still the best approach, the best model that will fit into real world examples, all right? So we talk about denormalization just to give you some example of most common exceptions you will have. Outside those exceptions, 95% of the chance, you still want your model to be third normal form compliant.